Hello everyone, my name is Pranav Singh and I'm from New York University. Today I'll be presenting my work on data efficient deep learning framework for segmentation and classification of histopathology images. This work has been in collaboration with Professor Jacopo, also from New York University. With this paper, we'd like to bring your attention the application of AI for autoimmune diseases, a topic that's been rather underrepresented in medical imaging. This is primarily because we have incomplete information about autoimmune diseases and there are no existing pipelines to collect data for autoimmune diseases as it is for other diseases. Because of this, the data set size for autoimmune diseases is fairly small. It is imperative to study autoimmune diseases in today's context because one, they are on the rise, and secondly, because existing AI techniques are either outdated or don't have an open source implementation. In our study, we focus on 198 sample data set collected from biopsies of patients suffering from dermatomyositis, which is basically an autoimmune disease. We focus on two tasks, segmentation as well as classification. For the segmentation task, we base our approach around UNIT and UNIT++, two of the most cited architectures for biomedical segmentation. In a normal supervised segmentation training pipeline, we have images and their corresponding masks, which are then passed through a segmentation architecture, which predicts its own sets of predicted masks. A loss is computed between the predicted mask and the ground truth mask to figure out loss between them, which is then used to fine tune the network to make better predictions for future. This usually gives good performance when the sample size is good enough. But in our case, we saw this was that there was more performance which could be extracted. To do so, we propose a novel segmentation post-processing method known as autoencoder post-processing or APP. In this, we basically use the normal segmentation or supervised segmentation architecture and then pass the predicted masks through a set of autoencoders. This autoencoder then predicts the mask, and a reconstruction loss is then computed between the predicted mask and the ground truth mask to add more information to the existing loss. Based on these two losses, we fine-tuned the network, and we found that doing so, we improved our segmentation performance by around 8%. Moving on to the second task, which is basically the classification task, we have optimized our approach for both CNNs and transformers, as well as for different kinds of classification tasks, such as binary, multi-class, and multi-label classification. We've also taken into account the imbalanced nature of medical imaging data sets, and this approach has helped us improve our classification performance by as much as 25% over existing approaches, existing state-of-the-art approaches on the autoimmune data set. We hope this framework could also be used for other medical imaging datasets and catalyze research not only for autoimmune diseases, but also for other fields suffering with the lack of data. Thank you.